So it says, if you were asked what's the one word that best describes what calculus is about, the best answer might be limits. So that's why this is always the first unit of a calculus course. So it says the first part of the course is mostly about derivatives, the rest is about integrals, but those are both limits. Near the end of this course, we'll look at infinite series. We actually already did look at infinite series, but they are dealing with limits. So they are the foundation for most of the other important concepts in calculus. And then this is our own Dr. Loynd here. The well-known Eagles song, Take It to the Limit, has the line, take it to the limit one more time. For better or for worse, the number of times we will take it to the limit will seem limitless. Let's build a good foundation for our study of calculus. So we're taking the limit all these different ways. And then I did put on here, we're going to have a summative assessment. And then we've got kind of 3 days built in for final exam review. All right, so here we go. So this is just what is a limit. And I'm going to say the definition of a limit every day this week so that you know what a limit is. So it says, a limit is a value that a function or sequence approaches as the input value approaches some value. So a limit is a y value that the function approaches for some x. So if you want to add that in, basically all limit is a y value the function approaches for some x. Limits are essential to calculus. They help define continuity, derivatives, and integrals. All right, so it says, let's think about one place we've already seen limits. This is the geometric sequence that some people are taking a test on right now. How would I do 80 times 1/2 to the n minus 1? If we were going to list the first 6 terms of the sequence, that would be what? 80 times 1/2 would be 40, 20, 10, 5, 2.5, right? I'm cutting it in half each time. So how would I find the infinite sum? Infinite sum is our formula from this last test, right? A sub 1 over 1 minus r. So I take the number 80, divide by 1 minus 1/2, and what do I get as the infinite sum? 80 divided by 1/2 is how much? 160, because it's really 80 divided by 1/2 is 80 times 2. If you start adding these numbers together, I'm already at what? 80 plus 40, 50, 60, 77.5. So I'm at 157.5 already. So do you see how that's going to approach 160, right? I'm going to keep adding little slivers together. So it says, why is this a limit? Because it never actually gets to 160. So it gets to 159.9999, but never actually 160. So it's a limit because it's approaching, right? So a limit is what y value does it approach? So it's approaching, but it never actually gets to 160. We just say that it converges to 160 because 159 with 0.999 repeating, we say is 160. And it says these are all the strategies we're going to look at: substitution, simplifying, conjugate. We're actually not going to look at properties of limits because we don't have enough time. Trig and dominant forms. So there's a bunch of different strategies. And the first one is just substitution. So it says just use simple substitution. The simplest type of limit involves a predictable function where you could just substitute it in the x value. You may think, why bother? But play along because it'll get more interesting. So if this is just introducing you to limit notation. So it says evaluate the limit by substitution, sketch a graph, show that the graph approaches the same value from the left and the right. So it says, what is the limit as x approaches 2 for this function? So 2x plus 1. When I plug in 2, what do I get? 2 times 2 plus 1 is how much? What do I get, Ava? 2 times 2 plus 1. What do I get? 5. So the y value it approaches is 5. So it says, hey, let's graph this line, right? The line y equals 2x plus 1. Here's my line. And the line continues forever. And what is the y value? The y value is 5 when x is 2. The graph is approaching it from both sides of the x-axis, right? So all a limit is a y value of a function. For a linear function, you just plug in x and generate y. So all we're learning today is, hey, we can use substitution. Then we're going to learn when substitution is going to fail. But you always start with substitution. All right, so what about in a quadratic function? We can find the limit also by substitution. If I plug in -1, -1 squared minus 3 is how much? So this is +1 minus 3, so -2. So I like this unit because it's a good review of, hey, I got to graph a quadratic, got to graph a linear function. So let's see, this is x squared shifted down 3 units. So it puts the vertex at -3. And do you remember for a parabola, over 1, up 1, over 2, up 4, 2, 3, 4. So kind of just refreshes your memory on how to graph some of our big functions. And then you can see when x approaches -1, right? Here's my y value. My y value is sitting there at -2. And it's approaching the same point from the left and the right. So that's going to be important later on. Later on, we're going to see graphs that do not approach the same point from the left and the right. All right, you're going to try to evaluate 3 and 4. So plug the, you don't have to graph them. Just plug in the x value, generate the y value, see what you get. So for this first one, I do 2 cubed minus 1. So 8 minus 1, the limit is 7. It's approaching 7. And the second one, I'm going to plug in -2 for both of these x's. So let's see, -4 plus 1 is -3 on top. -6 minus 2, -8 on the bottom. So +3/8 is the limit. Is that what other people got? All right, so those are the easiest type of limits. Plug in x, find y. So now it says level 2, so it gets a little bit trickier. It says sometimes the substitution that we wish to make is illegal because it makes the denominator 0. So for example, right here, if I want to take the limit as x goes to 2, 2 minus 2 in the denominator gives me 0. So it says we could factor the numerator and denominator first. This is a good review of rational functions, right? Our unit 2 this year was rational functions, and we had to factor and cancel to find the wholes. So we're going to just practice factoring. Difference of squares, x minus 2, x plus 2. X minus 2 is sitting in the denominator, and that canceled out. So now I can actually do the substitution and plug in 2 for my x. Right? The limit that I wanted to evaluate was when x is 2, what is the function approaching? It's approaching a whole. But what is the y value of the whole? 2 plus 2 equals 4. So the overall limit is 4. And what this would look like on a graph is actually a straight line with a hole in it. X squared minus 4 divided by x minus 2. So because the denominator canceled out, it's really a straight line with a hole in it. The only way you can see the hole is by going into the table. And it says there's an error at 2. So you can't see the number 4, but you can kind of see 2, 3, 5, 6, 7. So you can see that 4 would have been in that slot. So I like that this unit reviews kind of holes. All right, substitute 2 in. We just did that. Okay. So now then it says, look at a graph of the original function. Do you remember that this situation is a whole? So we just did all that. All right, so this says, now you try a couple. So it says, try direct substitution first, and if that fails, try factoring and canceling. All of these can be factored using the diamond, so they're not like extremely challenging factoring problems. But see what you remember. This is a good unit to review some of those factoring skills if they're rusty. So take a minute, try factoring 6 and 7, and then try canceling and plugging in those x values. I'll give you a couple minutes to try those. See where you get stuck. All right, I'm going to talk through them. I can plug -1 in, no problem, and just evaluate. So if I plug in -1, I would get 1 minus 5 plus 6 in the numerator. And I would get, I would get 1 minus 6 plus 8 in the denominator. So what's that give me? 2 over 9, 3. Anyone get 2/3 for the first one? Or did you try factoring it instead? I think that's what I get. Oh, because you put a negative here. Right. Okay, so 2/3, that one I could do by substitution. When I try to plug -2 over here, I end up getting 0 in the denominator. So this is the problem that you need to actually factor. So you can use the diamond method. We're looking for the factors of 6 that add up to 5. So x plus 2 and x plus 3. And in the denominator, we're looking for the factors of 8 that add up to 6. So x plus 2, x plus 4. So you can see that that x plus 2 factor cancels out, allowing me to now plug in -2 for x. So now I can actually evaluate the y value. I get -2 plus 3, positive 1 on top, and then -2 plus 4, 2 on the bottom. So the answer for that one would be 1/2. So both of those are substitution. This one you have to cancel first. So those are your first two strategies on limits. So this next page says, what about when substitution doesn't work? So it says, if limits can be found so easily by substitution, why don't we use it all the time? Unfortunately, we can't. So here are two functions in which the methods by substitution doesn't work. This is the same problem from the front page. I'm just going to write down that the factors were x plus 2, x plus 3, and then x plus 2, x plus 4, just so I can start with it in simplified form. So do you see how when I plug in -4, I can't do it? It's one of the asymptotes of this graph. So this is a good review of how to graph a rational function. So let's graph that it has a vertical asymptote at -4, right? Because that's where the denominator is 0. Do you remember what the numerator tells you from rational functions? It's actually your x-intercept. So I have an x-intercept at -3 because that would make the numerator 0. So I'm going to plot my x-intercept at -3. To find the y-intercept, remember you plug in 0 for the x's. You'll have your note card anyway for the final exam. We'll have a note card or a cheat sheet with these rules, but when I plug in zeros, I get 3/4. So my y-intercept is at positive 3/4. And then your asymptote, remember you compare the numerator and the denominator. These both have a linear factor of x, so they tie. So you strip the coefficients. So 1x over 1x would be 1. So this has a horizontal asymptote at 1. So this side of the graph is here. I could plug in another point, but just for the interest of time, the other part of the graph ends up being over in this region. So it says, let's do an analysis down underneath here. It says, do an analysis of the right and left-sided limits. So this is a different notation. You see how it says x is approaching -4 from the plus? And then on this one it says x is approaching -4 from the minus. That means from the right or from the left. So if there's that superscript plus or minus, that's important notation. So a right-sided limit is use your right hand. I'm to the right of the asymptote. The graph is pointing down. So the right limit is -infinity. And then when I look, the left limit is pointing up, right? It's up on the left side. So the left limit is +infinity, -infinity, +infinity. Are they going to the same place? They're not. So what we say that the limit is that the overall limit does not exist. So DNE is calculus language. You're going to see a lot this unit. DNE stands for does not exist. It's not no solution. It's not undefined. In limit world, we say DNE does not exist. So I'll show you one more example like that. So I go all the way up here to example 9. When I try to plug in 2, I can't do it. There's nothing to cancel. So I'm going to show you how to sketch this graph, and maybe rational functions will start coming back to your brain, just like factoring will hopefully come back to you. X approaches 2. I have a vertical asymptote at 2, so that's the problem, right? X can't get to 2 because there's a vertical asymptote. If I go through those steps again, the numerator is 1, so there's no x-intercept. The denominator is bigger, so there is a horizontal asymptote at 0. That's why there's no x-intercept. And the y-intercept, when I plug in 0, is -1/2. So on my graph, the y-intercept's at -1/2, and I can draw my elbow here. The other elbow's up here. If you don't believe me, you could plug in a value for x. So what's the right side doing? This time, the right side is actually going towards +infinity. So down below, when it asks you what the right side is doing, you can say +infinity. The left side up here is going towards -infinity. So they just flip-flopped, right? This time a different side is going up or down. And then so the overall limit, DNE, does not exist. So if my arms are pointing in different directions, then the graph doesn't know what to do. So it can't be approaching the same value. So we just say the limit does not exist. And this we're going to get into more, and on this test, I'm not going to be assessing graphs of rational functions. Like you'd have a calculator or your set of rules, but it's good to bring back some of the knowledge from this year. All right, so take the last few minutes. I'd like you to try these by substitution. So almost every single one, you can just plug in x and see what you get. If not, you could try factoring it and canceling it. And last resort, maybe look at the graph and see if there's an asymptote. So you are trying the guided practice for a few minutes on your own. All right, so you should have tried the guided practice on your own, and now you're trying to plug in 100. You get 299. When you plug in -5, you get 25 minus 15 minus 4. So 25 minus 29 comes out to, no, minus 19 comes out to +6. When you plug in for 80, the square root of 81 comes out to just 9. Here, when you plug in -2, you get -4 in the denominator. You get 4 minus 4 minus 8. So you get -8 divided by -4, so +2. Did anyone get +2? Is that what you got? Okay, you're checking me as I go. 5 you can't do until you factor. So this factors into x plus 4, x minus 2, x minus 2 on the bottom cancels. When you plug in +2, did you get 6? Okay. On number 6, the problem with this one is when you factor the denominator, x minus 2's cancel, but when you go to plug in -2, you still have 0 in the denominator. So if you looked at the graph, you'd have one of these types of graphs going in opposite directions at that asymptote. So this is a case when the limit dne does not exist. What'd you say? Not sure. Double check that one. Number 7 is another case of DNE because the denominator is going to be undefined and it's going to be type of asymptote that we can't get rid of. So this one should have also been a problem. This one came out to what? 10 over 100, so 1/10 or 0.1. This is just e cubed, so you can do e on your calculator. Second e raised to the third power. 20.09 if I rounded it. Did you get that? And then this one just comes out to negative 1/2 when I plug in 0 for x. So you've just solved limits by substitution.